Welcome, math fans. In this lecture, we're going to start our discussion with the natural numbers by asking one of the most important questions that spans back centuries, even millennia, to the first civilizations, and that is, what even is a number? And it's this concept that we take for granted, and in order to answer that question, the first thing that I thought of is an atom. And so over here, this is not an atom, but is composed actually of several atoms in a molecule called xenon hexafluoride, which ends up being about 9 times denser than air. It gives you that Darth Vader voice. So we don't really think of things in terms of atoms, we think of things in terms of matter, or the things that you can perceive on a daily basis. So I argue in the same exact way that numbers themselves don't really tell you enough. It's really the collection of all numbers into what are called systems, or as I might even refer to them as sandboxes, that have special properties that you can kind of look at under a microscope and do some really cool things with. So I go back to atoms a lot, and the idea is that, atoms really build tangible things. And just like atoms build tangible things that we call matter, numbers build tangible things that we can do and answer practical questions on. So the first thing, of course, is to talk about what natural numbers even are, and they're usually given the symbol n with these little bars right here. And really what it is it's a collection of what we call the counting numbers, 1, 2, 3, 4, and so on. Again, I'm not going to teach you everything about this, but the idea is that you can get each next number by adding 1 from the previous number. So you can define them kind of recursively. Okay? And to be honest with you, numbers are absolutely useless without telling you some things that you can do with numbers. Okay, so let's start out with maybe talking about the first important thing that you can do with numbers, and that is this operation, which is called addition. So if I wanted to add the natural numbers 2 and 3, for example, the first thing that you might notice is that 2 can be written as maybe 2 vertical lines like this, and 3 can be written as 3 vertical lines. And the most natural thing to do with those two things is just to combine them. In fact, this is how the first civilizations actually counted. If you think back to, shepherds way back in the day, in order to count livestock, which was incredibly important to make sure they had the same amount of sheep, some maybe claimed they used rocks and they moved piles of rocks. Others used a bone, and they used sharp tools during the Stone Age and onward in order to carve out indentations in the bone. Okay, so 2 would have this many indentations, 3 would have this many indentations, and to combine them, you would just say that 2 plus 3 would be represented like this. And of course, we have a name for this. This is, of course, 5. Okay, and of course, obviously, having all those vertical lines made it hard to keep track of that, and that's where the tally was invented, a little diagonal slash in order to group those together visually. All right. So that's the first thing that you can do. And of course, it's really the most important thing that you can do. But sometimes you want to add a single number, like maybe 4, for example. You might want to add 4 several times. And it would be cumbersome to write out exactly how many times, because, for example, you might want to add 4 like 100 times. And then how are you supposed to represent that? Okay? And so really what you would do, let's say that in this context, I might have, let's just stick with 100 copies of 4, and I would like to combine all of those. Really what we would say in this instance is we would define another thing that we can do with natural numbers called multiplication. Okay, where it doesn't really matter, but we'll just say this number represents the number of copies, the number of copies of the first number that I would like. And this, of course, should be 100. I don't know why I put 5 there. So I want 100 copies of 4, so I'm going to add 4 to itself 100 times. So again, that means that I have 4 here and 4 there, and 4 there, and I just keep going and going, and then I just count out how many tallies I have in total. So that should be a pretty natural way of thinking about this. Now, these properties of numbers can also be represented with dots, and they have very specific laws that they obey, and these are going to be the laws of arithmetic. So I'm going to write these down, and then we're going to discuss them. So the first law of arithmetic you might have called the commutative law, okay? And this is the commutative law for addition. So commutative for addition. And it basically states that something like 2 plus 3 is going to equal 3 plus 2. And from the dot model, it's pretty clear, right? We're combining the same number of dots. I can choose to break that up in however way that I want. The second law, sometimes called the associative law, and again, this is specifically the associative law for addition, states that it doesn't matter if you have multiple additions, it doesn't matter the order in which you do them. Okay? So for example, I could choose to do 2 plus 3 first. Out of 2 plus 3 plus 1, I could choose to group up the 2 and the 3 first. Or I could choose to group the 3 and the 1. This is different from commutativity because commutativity says you can flip them. Associativity says that you can tackle this first and then this. So it establishes some sort of order in which you do the additions. Okay, so you see it pretty clearly right here. If I have the 2 and the 3s and then the 1, I get the same thing in the end, whereas if I had the 3 and the 1s and then the 2s, again, it's all the same number of blocks in the end. Okay. Then I have the exact same laws, but this time for multiplication. So this would be the commutative law for multiplication. And just as a convention, instead of writing this dot, you just put the things right next to each other. So the natural number a times natural number b equals b times a. And the reason for this is, just as an example, let's suppose that I have the number 2 times the number 3. Well, remember what that means. That means I want 3 copies of 2. So I want, 1, 2, 3 copies of 2. And if I smash those together on a grid, I could just as easily, instead of breaking it up, this way, I could also choose to break it up this way. And I could also choose to have 2 copies of the number 3. Okay? And I get the same structure overall. I get an A by B structure, a lattice, a grid of dots. Okay. Then I have the associative law. So this is the associative law again for multiplication. And just as an example, if I have 2 times 3 times 2, I want to show that that's the same thing as first taking 3 times 2 and then multiplying that by 2. Okay, so in this first picture of dots, what I have is I have 3 copies of 2. Right, that's what this means. I have 3 copies, 1, 2, 3 of 2, and then I have 2 copies of this overall structure. So that's what this 2 means. I have 2 copies of 3 copies of 2. And again, instead of dividing it up like this, I could divide it up vertically like this, and I essentially get this structure, which is I get 2 copies. Okay, so I get 1, 2. I get 2 copies of 2 copies of 3. So this says 2 copies of 3, and that's what this thing is, right? This whole thing right here is 2 copies of 3, and then I have 2 copies of the 2 copies of 3. And the last law that I have is I have the distributive law, which is significant because it combines the addition and multiplication operations. And what the distributive law states is that the overall structure, when I'm trying to multiply and add, is maintained by whatever's inside the parentheses. So in this case, addition is inside the parentheses, so addition is going to be the big picture of what's happening. I'm going to be adding 2 things together. But the distribution comes from the fact that I am essentially distributing multiplication by a across to both of these terms. That's why I have a times b over here and a times c. So I can't prove any of these. These are just facts of life. Okay, and so to show you an example, we're going to show why 3 times 2 plus 4 is really going to be equal to 3 times 2 plus 3 times 4. So I have 2 and 4, that makes 6. So I have this thing over here. But this thing, remember, means that I want 3 copies of that. Okay, so I have 1, 2, and 3 copies. But you'll notice that I really have two, I could break this up into 2 parts. This thing right here is nothing more than 3 copies of 2. Okay, so 3 copies of 2. And this thing right here is nothing more than 3 copies of 4. So I do indeed get the distributive law. As well as all of those arithmetic laws that the natural numbers have to have, they also have another very, very important distinguishing property, something called order. And what order means is that for any 2 natural numbers, a and b, you have to have one of the following. Either a is bigger than b is bigger than a, or a is equal to b. And it's pretty easy to figure out that if I have a system like 1, 2, and so on, the way that I define the natural numbers is just to say that each natural number is 1 more than the previous one. So we can define it recursively exactly as I mentioned in the beginning. And so clearly, 3 rocks is more than 2 rocks. However, how do we kind of do this a little bit more systematically? Well, we can go back to the dots, and we notice that if I have a on top and b on bottom, we know that a is bigger than b if I can add some number of dots to b in order for them to equal out. So maybe we'll call this c, for example. So we say that a is bigger than b if for some c, again, natural number, for some natural number c, b plus c is equal to a. And of course, I shouldn't use symbols. So I should say, equal to a. And this is pretty natural, right? If I have a bunch of rocks over there and a bunch of rocks over here, and I don't know, we'll just line up the first pile of rocks and line up the second pile of rocks and figure out if I can add some rocks to this in order to equal the number of rocks over here. And this works with scales as well, right? If I have like a balancing scale, put A on one scale and B on the other, and if it's kind of close, then continue to add identical bits of things to B and see if you ultimately get the scales to balance. So this is a very natural thing to do, okay? And this is a very natural definition of if one number is bigger than another. And this also works for equality as well. So for example, if I have equal numbers of dots, we'll say, this, then I can say that 2 numbers are equal. I can say that 2 numbers are equal. So equal if I can't add anything to either the top or the bottom, either to A or B, in order to get them to balance out. Okay, and if I'm being honest, this method is somewhat practical for maybe numbers 1 through 10. Okay, so in other words, this does work for small numbers. But let me pose a problem to you now. So problem, how can I compare the numbers 2 to the 100 and 6 to the 30th? And I'm going to explain what this notation is, of course. remember that the multiplication operation was just adding copies of something. Well, if I wanted to multiply copies of a number over and over again, then we might want to notate that. So let's say I wanted to multiply the number 2 by itself 100 times, and I wanted to multiply the number 6 by itself 30 times. Then I would notate that using something called an exponent, which again is completely natural when working with the natural numbers. And that's what this thing is here. So we have that this right here. That's called the exponent. And this thing right here, the thing that you're copying, that's called the base. So if I multiply 2 100 times and I multiply 6 30 times. Now, in theory, you can do this. You can do this by hand, and here's how. If I wanted to take this, the first thing that I would do is I would use the associative rule of multiplication in order to group these as follows. So let me do maybe one more. So times 2 times dot, dot, dot. What I would say is I would first group these up, then I would group these up, and then I would group those up, and then so on and so forth. And I would take 2 times 2 by adding 2 copies of 2, so 1 plus 1, and then plus 1 plus 1. Then I have 4. And then I would have 2 copies of 4, and then I have 2 copies of 8, and then I would continue doing this 100 times. And then I would do the same thing for here. So you could do that, and you might argue, well, I have a computer that can do it too. Okay, but pretty soon your calculators aren't even going to be able to evaluate numbers like this. And so what's a good way of quickly comparing those two numbers? So we have to kind of go back and maybe fix this definition. There's nothing wrong with it per se, but we're just going to modify and think about the order of these numbers a little bit differently. So here's how we're going to think about it. So I'm going to take the same exact picture right here, okay, and I actually forgot. I think I had, well, we'll just do 3, doesn't matter. And we're going to call this number A. Then what I'm going to do is I'm going to take this number right here, and I'm going to call this B. And maybe we call these dots. And maybe we call these anti-dots. And what anti-dots do is anytime they come into contact with the dot, they completely eliminate. You might think that this is a little ridiculous, but this actually happens in nature. You have matter, things like electrons. You have antimatter, things like anti-electrons. When you have an electron and you add an anti-electron, they annihilate, destroy each other, cease to exist. Okay? And so really what this picture illustrates is that here, when I combine these together, the blue and the red dots here when I line it up cancel, and here the blue and the red dots cancel, and I'm left with more of A. And so A had to be bigger than B. Okay? So what we're doing is we're effectively combining, we are effectively combining A and B. We're effectively combining A and B. The problem is, A is a natural number. And that's something that we're used to. We spent the whole video talking about it. But I'm going to argue to you that B actually isn't a natural number. And the reason that I know that B is not a natural number is because when I performed this weird addition between 3 and supposedly 2, I got 1. Whereas you know that I actually should have gotten 5. So this can't be a natural number. And so what's really going on here? Well, it turns out that I just invented a new kind of number that is the opposite of the natural number. And what do I mean by opposite? Well, let's take A, which was 3, and you know that 3 is really just the same as 1 plus 1 plus 1. And what I've just done was I've invented a new number B which is really -1 and -1. So this -1 completely cancels out the 1, and I don't have anything left. And so this ends up being a -2. Why a -2? Well, if I had a +2 for A, that would completely cancel out with the -2. Okay? And so you can see this because if I take A plus B now, if I take A plus B, what that's going to be is it's going to be, well, A was 1 plus 1 plus 1, plus B was -1 plus -1. And remember, I have the associative rule, which technically only works for natural numbers, but maybe it'll work in this case. And so what does the associative rule say? Well, it says that I can really just put the parentheses anywhere that I want. So I'm going to put them right here, because what I have now is that these cancel, and then these cancel, and then I'm left with 1 left over. And that 1 is a natural number. It's the positive number 1. Okay? So let me give you another example. It's a bit trickier. So another example. What happens whenever I take, say, -7, and I try to add to that -5? Well, what does the number -7 represent? Well, it represents 7 anti-dots, so to speak. So I have, -1 plus -1 plus so on and so forth, and I have that, I'm adding that 7 times. Okay, and then I'm adding to that 5 more anti-dots. So again, I have -1 added to itself. And this is 5 times. Which means in total, I have 12 anti-dots. And since it's an anti-dot, we say that -7 plus a -5 is equal to -12. Meaning, if I had 12 regular dots and I add that to 12 anti-dots, then I would get nothing left over. Okay? Now, an alternative way of viewing this, by the way, from physics, is suppose that I have some sort of path, and maybe you start walking from your house, and you have some sort of way of measuring unit distances. Okay? So a distance like exactly 1 meter. I can't have fractions because we're not talking about fractions. Okay? And so what I really have is I have a situation that looks a little something like this, where I first start by walking 7 units to the left. Okay? And you should first establish what the positive direction is. Okay, so if I'm increasing, maybe I'm going to the right or something like that. So I think it's pretty natural, since the natural numbers start from 1 and we usually read left to right, that this is usually perceived as positive. So if we're going the other direction to the left, then we might be taking, 7 steps to the left. So maybe I'll do it like this. And then we took another 5 steps to the left. And so all in all, we just took 12 steps to the left. Now, there's a bit of notation, and notation usually comes about out of laziness. And so a lot of times what people will do, instead of writing -7 plus -5, is they will really write -7 minus 5. And what this means is I have -7 and then I have -5, and I want to combine those two. It's really, really lazy, and it's confusing because some people call this operation subtraction. But in my head, subtraction does not exist. What exists is addition, and you're really adding dots and anti-dots. So let me give you an example of where this turns confusing. Let's suppose that I have negative 3 minus a negative 5. And maybe from grade school you memorized, oh, a negative negative is a positive. Really think about what you're doing here, though. So this is an example. So what's happening here is what I'm really saying is I want to take negative 3 and I would like to add to that an anti-5. So what does that actually mean? Well, remember that this means that I need 5, positive 5, to cancel that out. Which means that this thing would mean that I actually need minus 5 to cancel it out, because it's the inverse of that. So it's the inverse of the inverse. Another way of thinking about it, you can almost think of this negative sign as a way to transform blue dots into red dots. So if I start out with a blue dot and I make it negative, then it's a red dot. And if I make that negative, I go back to blue. So I still have a positive number. But really, it is the inverse of the inverse. So I go back and forth. Okay? So really, that's why I can write that as negative 3 plus, and then this thing ends up being a 5. And then when you compare the 3 red dots and the 5 blue dots, I have 2 more blue dots. And so this is going to end up being 2. Now, there's one more problem with this. So right now, we've established that there are things called natural numbers. And then we have these odd things, which, I don't know, I might call the negative, the inverse of the natural numbers. But here's a question for you. What happens whenever I have this situation? I'll make it simple. What happens in this situation? Well, you might say the blue dots completely cancel out with the red dots, and what I end up getting is, and I hear this all the time from students, nothing. I would not call that nothing. For example, if an electron collides with an anti-electron and completely annihilates it, I wouldn't call that nothing. I would call that pretty darn cool. The fact that there's nothing left over is still something. And so in math, we actually represent that with its own symbol, and we call this an identity element, or 0 in this case. Okay, and what 0 really represents is it represents the leftover between taking 2 and adding negative 2. Because remember that with natural numbers, anytime you took one natural number plus another, you had to end up with a natural number. And we even saw that with blue and red dots, in most of the cases we considered, we either had more blue dots or we had more red dots. So with the natural numbers and the inverse to the natural numbers, we still, for the most part, had this containment idea. It's called closure. But if I have equal numbers of red and blue dots, I still need to be contained. So I still need that to be something in my system. Okay, so we define this to be 0. And all 0 really means is if I have any natural or inverse natural number and I add 0 to that, I can add it to the right or to the left. I don't change the number at all. Okay, so just to summarize what we talked about, we started with this set, which we called the natural numbers, which were starting at 1, 2, 3, and so on. But then we discovered that if we wanted to compare two numbers, we really needed a better, more complete system. Okay? And so what we really have is we really have a bigger set that has to contain the natural numbers, and this goes off, but it also has to contain the inverses to all of those numbers. So every number 1, we also have to have an anti-dot to that, as well as -2, -3, and so on and so forth, kind of backwards. But we needed one more number in case there just so happened to be equal numbers. And so to compare that, we say that, we have a 0 element here. So just to specify, these would be called positive. These would be called negative. And this identity element we call 0, which for the longest time was not incorporated into math. I think it was Brahmagupta, Indian mathematician, who really established that. Okay, and we call this set of numbers Z. And the reason that it's called Z has to do with the fact that it's a German word, Zahlen, okay, which is German. This is German for numbers. And I do think that it's a little interesting that we use a Z to represent this system, and we also use a Z to represent 0. I know that there isn't really any relationship, but I am curious about perhaps the origin of 0. I know in Spanish it's with a C, but that is interesting. And so whereas this is the natural numbers in English, we're not going to call this a Zahlen. Really, we're going to call these the integers. Okay, and now that we have a whole system, this is actually more inclusive than the natural numbers. Not only do all the same arithmetic properties hold, so go back to 1 through 5, I promise all of those still hold in the integers, but we also have a lot of other properties that I'm not going to discuss at this time, but it's a way, way better system. Okay, and so the last thing that I'll do is I'll talk about comparing, and we'll finally kind of go back to that problem that I established. So with comparing, what I have is 3 different situations. All right, I could have that A is greater than B, and to symbolize that, what that really means is that if I take A and add the inverse of B, that I end up with a positive number. I want you to think about that for a second. So imagine that A composes of dots and B were the anti-dots. If A is greater than B, there are going to be more dots. Okay, so we say that it's a positive number overall. Okay, and so notation-wise, what we have is that we say A greater than B. Okay, where this symbol right here, greater than, that is this symbol. And to say that A plus the inverse of B is positive, what that means is that A, and I'll use the lazy notation, A inverse of B is positive, which means that it is bigger, it's greater than 0. Because remember, the integers go off positive here, and then anything to the left was negative. Okay, and likewise, I'm not going to spend as much time on the other cases. If B is greater than A, that means that A is smaller or less than B, which means that if I take this quantity right here, this is going to get me a negative. This is going to get me a negative number, which means that A minus B is going to be less than 0. Finally, if A is equal to B, what that means is that A plus negative B is going to be 0. It's going to be this identity element. Okay, so what we say for that is we say that A minus B, and the symbol is equal to 0. Right? So this symbol right here, that's the equal sign. Now, the final thing, I'll go back to our problem, and now we have a way of answering it now. So remember that I wanted to compare the numbers 2 to the 100 and 6 to the 30th. And I said if you wanted to, you could manually do 2 to the 100 and 6 to the 30th, or you could at least type them in a calculator and you could try to compare every single digit. Alternatively, what you could do is you could just take the difference, or you could just take 2 to the 100 plus the inverse of 6 to the 30th. On a calculator, we call that subtraction. You just take this number minus this number. And if we get a positive number, we know that this is bigger, and if we get a negative number, we know this is bigger, and if we get 0, they both have the same size. Okay, and it turns out that if you type this on a calculator, you're going to get that this is going to be positive, which means that this number is bigger. And there's a way, if you have properties of exponents, to prove this to yourself really quickly without even using a calculator whatsoever. So I encourage, if you know how to do that, then feel free to do it in the comments. But otherwise, that's all I have for you this lesson. This was an introduction to the natural numbers and the integers. Next time, we're going to talk about bases and how 10 is not as important a number as people lead you to believe. Hope to see you there, and have a great rest of your day.